Hi, everyone. Thanks for coming. Before we get started with today's seminar, just a quick announcement that the next seminar in our ORI anniversary series is going to be in the new year on the 19th of January. You can find out more details about it and the future talks at ori.ox.ac.uk/events. So on to today's speaker. It's my immense pleasure to introduce Dr. Larry Matthies. Larry is the technology coordinator in the Mars Exploration Program Office at the Jet Propulsion Laboratory, and he previously supervised their computer vision group there for 21 years. His research has focused on perception systems for autonomous robotic vehicles for land, sea, air, and space applications, and his work has affected every US Mars surface mission since Pathfinder in 1997. So Larry is a fellow of the IEEE, and he obtained a PhD in computer science from Carnegie Mellon University in the US, a master's from the University of Waterloo, and a bachelor's from the University of Regina, both in Canada. On that last point, I can also share that he gives a very personalized tour of Regina, Saskatchewan, in the very unlikely event you ever find yourself with that opportunity. Today, Larry's going to share with us some of the successes and highlights from NASA's most recent mission to Mars, the Perseverance rover, as well as some of the future challenges in planetary rovers. So please, Larry.
Thank you very much. Thanks for the introduction and the invitation. It's a pleasure to be here. I'm going to just turn my video off during the presentation, so I'm not distracting myself, and I'll turn it back on when I'm done. So this talk, by the way, can you just reconfirm you can hear me well enough?
Yeah, we can hear you quite well. Your slides aren't up yet, though.
Yeah.
Okay.
All right, slides up and in presentation mode. How's that?
Yep, we see presentation mode.
Okay, and let me check for a pointer here. Like I was telling you before, I usually use WebEx. So, well, I think this is good enough. Let me just get going.
Okay.
And whoops, I didn't mean to advance just yet. So this talk is a slightly updated version of a presentation I gave for the RSS conference last summer. So if you've seen that, I apologize for the duplication. The title, In Situ Mobility, that's a term that we use in the planetary exploration business to moving around on the surface or above the surface for planetary exploration. Most of the talk is focused on what's new from a robotics perspective in the 2020 Mars mission, in the Perseverance rover and the Ingenuity helicopter. But I do have some material at the end of the presentation about what we see as next up for Mars and other areas where we do in situ mobility. So the moon and Saturn's moon, Titan, also has an atmosphere, in fact, the densest atmosphere of rocky surface bodies, well, not rocky, but solid surface bodies. So I've got a couple of slides at the end about aerial mobility on Titan. The graphic on the cover here shows the moment of landing in an artist's conception. So that's the descent stage with the propulsion system at the top, and it lowers the rover on cables. As soon as the rover touches down, the cables get cut and the descent stage flies away. So let's see, my slides aren't advancing. Why is that? There we go. Okay, so I'd like to go over a few basic facts about Mars. So it's about half the diameter of Earth and twice the diameter of the moon, about 1.5 times as far from the sun as the Earth, gravity about the third of the Earth. For helicopters, an important fact is the density of the atmosphere at the surface is about 1% of the Earth. Pretty wide temperature range from the numbers you see there. And length of a Mars day is just a little bit longer than an Earth day. Why do we go to Mars? So these 4 blocks on the left illustrate the themes that have motivated NASA's exploration of Mars since the beginning. So looking for signs of either previous or possibly current life, and understanding its climate, exploring its geology. Those really all, in my view, they're about understanding. Let's see, I don't know why this has apparently timing on. You know what? I didn't expect this. This didn't happen when I was dry running it. So I'm going to have to mess with this and figure out what's going on. Okay, let me try that again. Okay, these three themes of look for signs of life, understanding climate, exploring geology, they're important really in understanding how did we get here. So how did the solar system form? How do planets evolve? Are we alone in the universe? And then given interest in human space flight, another part of Mars exploration is preparing for eventual human trips to Mars. And so starting in the decade of the 2000s, a unifying theme for that was follow the water. So water plays an important role in all four of those themes, and we're basically following signs of water or ice to explore all of those themes. So Mars has thick ice caps at both poles. At the North Pole, it's mostly water ice. South Pole is higher elevation, so it's a mixture of water and CO2 ice. There's abundant evidence from orbital imagery and from the surface that more than 3 billion years ago, there was a lot of liquid water on the surface. We now know that there's also a lot of ice buried in the mid-latitudes under the surface. And since the 2000s, we've had other themes. So we went from follow the water to explore habitability, which was looking to see, yes, there's water, but that doesn't necessarily mean it's habitability. So looking at the chemistry, the temperature and so forth to see if it was hospitable to life. We established with the Curiosity mission in the middle of the last decade that there were environments that were habitable 3.5 to 4 billion years ago. So then the theme switched to seeking signs of life. And that's what the current mission is all about. And then of course, also preparing for human exploration. So this graphic illustrates most of the US and international missions that have gone to Mars. Doesn't have all the rovers on it, but it's got most of the orbiters. You can see the progression of high-level themes across the bottom. Kind of in the middle, you see the Mars 2020 rover there. So an important part of its job is to collect samples, and it will leave them on the surface. And then there's a NASA European Space Agency collaboration working to develop a mission to go and retrieve those. The plan right now is to send a lander toward the end of this decade that will carry a sample fetch rover. So the US will build the lander, Europe will build the rover. That rover will go out and pick up the samples left behind by Perseverance, bring them back. They'll get launched into orbit in a small canister. And then there's a sample return orbiter to be built by Europe that will bring them back to Earth. China has also announced ambitions to do a sample return mission. Japan is right now building a mission called MMX to go to the moons of Mars. The UAE recently put its first orbiter around Mars. So I'll keep going here. This is a family photo, basically, of the US rovers. Sorry about my dog in the background. I just mentioned a few things. So Sojourner and the two Mars exploration rovers, Spirit and Opportunity, were solar powered. With the Curiosity and Perseverance rovers, they were too big for solar. And also we wanted to have the ability to go to higher latitudes where there wasn't enough solar power. So those were and are powered by radioisotope thermal generators. Another thing that's important for what we're talking about today is computing power. So Sojourner had an 8-bit microprocessor with no floating point, a 2 megahertz clock rate. Basically can't do a lot with that. From there, we progressed to Spirit and Opportunity having what was called a RAD 6000, which was an early PowerPC architecture, 20 megahertz clock rate, still no floating point, no L2 cache. In Curiosity and Perseverance, they have a PowerPC 750. Now we have finally floating point and an L2 cache, clock rate around 132 megahertz. And then with Perseverance, we've added an FPGA coprocessor. which does the low-level image processing for stereo vision and visual feature tracking for visual odometry for rover navigation. So with that, we were able to dramatically increase the speed of the rover. And that same FPGA coprocessor played a key role during entry, descent, and landing for precision landing. And I'll talk about that in a little bit. Okay, so short summary of what's new in this mission. The top two bullets are what's important from a scientific perspective. So we have more instruments and more sophisticated instruments than we've had before on the surface of Mars. And that's about searching for signs of ancient microbial life. We have a pretty sophisticated mechanical system to acquire samples, seal them hermetically in sample tubes and leave them on the surface. And we take planetary protection very seriously. So we want to make sure that with every mission, we don't want to be carrying Earth microbes to Mars. And with this mission, we don't, if there is any life on Mars, we don't want to contaminate Earth with it. So a very important consideration in the sample caching system. And then from a robotics perspective, three of the most significant items are the precision landing with a terrain relative navigation system so that we know where the descent stage is in the last 3 or 4 kilometers of descent. And that is used, we don't do onboard landing hazard detection with this mission. We map all the landing hazards with orbital imagery. And then the problem is transformed into a precision navigation problem. So if you know where you are during descent, I'm sorry, this is probably going to happen throughout the talk. It seems like there's timing advancement in the slide deck that I didn't realize was there. Anyway, we do precision landing to avoid hazards that we've previously mapped from orbit. We've got that FPGA coprocessor to enable much faster navigation and a smarter path planning algorithm. And then the helicopter, which I'm sure you've heard about. I'll talk about that. This is just a quick illustration of all the scientific instruments. So going clockwise from the left, there's a shallow subsurface radar for geology to map the subsurface down to about 10 meters depth. There's a zoom stereo camera system on the mast. The SuperCam has what's called a laser-induced breakdown spectroscopy instrument, which fires short, high-energy laser pulses and then images those in order to remotely estimate basically the chemical composition, the frequency of occurrence of different elements within what's targeted. There's a weather station. Out on the end of the arm, there's 2 spectrometers. So there's an ultraviolet spectrometer and an X-ray spectrometer. And what they are there for is to observe the mineralogy. So between the mineralogy and the chemistry, you can infer a lot about the rocks and the rock history. And then down at the bottom, MOXIE is a technology experiment to show that we can produce oxygen from the carbon dioxide in the atmosphere. And that's really feed forward tech demo, because if we ever do send people, we would need that kind of capability. Sprinkled throughout the slides, I've got some references to papers where you can learn more about the things that are talked about, and I can make this slide deck available later in case anybody wants it. Okay, so this is a video that illustrates the operation of sample acquisition, sealing up sample tubes, and storing them inside the rover. I'm not going to say more about that in the rest of the talk, but I just wanted to illustrate how this works. So there's a core drill in that big turret on the end of the arm, and it's got, I've forgotten how many now, but a set of interchangeable bits in case one stops functioning or we need to sample different types of materials. I think its drilling depth is 6 or 7 centimeters. So it grabs a core, then we need to inspect it to make sure we understand what we got. We hermetically seal it, and then we store it over on the left side of this image. We store it in a bank of cells inside the rover. So this is mostly, I think, quite a bit of basically open loop mechanism here. The arm itself does quite a bit of its operation over open loop, so it all had to be very stiff. And then, once we've got those samples, how do we want to get them eventually to a sample return lander? And you want that to be robust to every possible failure mechanism that you can imagine. And so there's a big engineering trade study, and it was finally decided that the most robust way to do that is just to drop the sample tubes on the surface at 2 different points in the mission. So we have 2 caches, if you will, of sample tubes on the surface. And later in this decade, the fetch rover will go out to, well, actually we'll do a pinpoint landing close to one of those caches and send the fetch rover to pick them all up and bring them back to the sample return lander. Okay, now let's talk about where we went. So the landing site is inside Jezero crater. That's illustrated in the false color elevation map on the left. And if you can make out the black ellipse, that's about 7 kilometers in the long axis. So we know that this crater was formed somewhere around, I think 3.6, 3.7 billion years ago. And we can tell that at some point it had a lake that was about 500 meters deep. And so this is an artist's rendition of the lake. And there was an inlet in this figure, at about 11 o'clock relative to the crater, and an outlet at about 3 o'clock. And we can tell from the orbital imagery that there was a delta formed at that inlet, which you see there. And so that green arrow is just the vantage point for this 3D rendering to give you a little bit more of a sense of what it looks like in 3D. And then those red X's show where Perseverance landed. And so really this kind of a delta and what it implies about the amount of water that flowed and the duration that water flowed, and the possibility for preservation of biological material. That's why we went to that landing site. But you can see here that compared to where we've gone before on Mars, which are pretty featureless plains, a lot safer place to land, this is a lot more hazardous place to land. So we needed new landing technology. So on the left here is an illustration of the 3 sigma landing error ellipses from the Mars Pathfinder mission forward. And so that's progressed from about 200 kilometers in the long axis for Pathfinder to 130 for the Phoenix and InSight missions. Curiosity is the first time we used a capability called guided entry that I'll talk about in a minute. So that brought the landing ellipse down to 15.5 or 25 kilometers in long axis. Some more improvements brought that down to about 7.7 kilometers. And then with the precision landing capability, we can target a landing spot to a few tens of meters within that 7.7 kilometer landing ellipse. And so guided entry is a technique where we've got this thing we call basically the aeroshell. By kicking out some weights out the back shell, we can create a slightly off center of gravity, which gives us some angle of attack. And then there are little retro rockets, not retro rockets, but little jets on the back shell that let us rotate this about the axis of forward motion. And so that lets us steer the lift vector. And so that lets us basically steer this thing during the hypersonic phase of entry before we deploy the parachute. And we have a pretty good knowledge of where this is before it enters the atmosphere, error on the scale of a few kilometers, and a navigation grade IMU. So that let us bring the error ellipse down from basically 130 kilometers to 25 kilometers. And then the parachute descent phase, only about 2 minutes long. For Curiosity, we deployed the parachute, and then we had that rocket-powered descent stage that dropped out of the back shell. And for Curiosity, we just pre-programmed what we call a divert to fly to the side of about 300 meters so that the parachute and back shell wouldn't come down on the rover. For the Perseverance mission, we added a camera to this whole descent sequence so that we could estimate position during descent and then use that position knowledge to avoid the landing hazards. So this illustrates the landing ellipse over top of a hazard map. And you can kind of make out the delta in the upper left and color codes landing safety here. So blue is where it's safe to land and all the other colors are where we don't want to land. So you can see that a lot of this ellipse was not safe for landing. And I think the divert range capability for Perseverance ended up being close to 700 meters. And it actually executed pretty close to the maximum range divert. And in the reconstructions after landing, we think the landing error was, I've forgotten the number, but it's a few tens of meters. Okay, so over here on the left is an illustration of that process. The orbiter imagery with the high-rise camera gets images with a resolution of 30 centimeters per pixel. We can use that to create elevation maps with a resolution of about 1 meter per pixel. Between the imagery and the elevation data, we can map the rocks and the slopes and craters, decide where it's safe to land. And then during descent at an altitude of 3 to 4 kilometers, this lander vision system in real time on board correlates descent images to the orbital map images to estimate position. And then there's an onboard trajectory generation algorithm that decides where to land. And that vision system was enabled by the FPGA coprocessor that's illustrated on the left, on the right, I should say, that uses a Xilinx Vertex 5 FPGA. I'm not going to say more about that today, but the papers that are cited at the bottom talk about the lander vision system and talk a little bit about the development of the FPGA system for rover, which does stereo vision and visual odometry. Okay, so here again is an illustration of the landing ellipse. The little blue token is where the rover landed, and the white lines illustrate the field of view covered by this panorama. So I'm just trying to help you relate one image to the next. So in that panorama at the bottom, from sort of the center to the right, is the main bulk of the delta. Over on the left, there's a kind of a remnant little mesa that's part of the delta, or was part of the delta at one time, and that's zoomed in. So that zoom camera on the mast took this picture, and there's just a scale bar there of 10 meters. So that mesa is something like 50 meters or so tall. Okay, so this, at the time of landing, this is what we thought the rover might do. So the white dot shows where it landed. There's an impassable region to the west. So we either needed to go south and around it or north and around it to get to the delta. What it's actually ended up doing was going south for a little ways to get into some of that area to take some samples. That's illustrated by the red. And it turned out that the helicopter was originally intended to be just a technology demonstration of aerial flight on Mars, but it succeeded and it continued to survive. And the science team decided it actually was very valuable as a scout. So it was used to scout this route for the rover into that area. Now we're coming back out of there and we're going to take the north way around to get over to the delta. So this image just illustrates all the cameras that are on the vehicle. There are front and rear hazard cameras, we call HazCams, that have very wide fields of view, something like 150 degrees. They're used for getting range data in the first few meters from the vehicle, which is useful for the sampling operations. On the mast, the mast cam Z is really used for science. So the navigation cameras that we call nav cams are about 45-degree field of view. Grayscale cameras we use for panoramic elevation mapping, for path planning, and for localization. We do localization by sending NavCam images to Earth and then interactively registering those with the orbital imagery to tell us where the rover is. There's a kind of a remote micro imager in the mast, in the turret on the arm. Okay, so what were some of the autonomous navigation challenges here? In order to achieve the science objectives, there was a certain amount of distance we had to cover. To be able to cover that in the amount of time available, we had to go a lot faster. So we had to have this FPGA coprocessor. Previous missions would basically stop and think and then do a blind drive of about a half a rover length and then stop and acquire more images and plan, do another short blind drive. For this mission, we had to do thinking while driving. So for the first time, we continue to drive while we're acquiring images and processing the images. You know, it's, I think, something we've done on Earth for a very long time, but this mission was the first time we've done that on Mars. As I mentioned, we had to have a path planner that was smart enough to straddle rocks instead of always going around them. And visual odometry lets us basically correct the position estimate for slip. So we don't have to be as conservative now as we used to be about slip. So the net effect is that with full autonomy, we can drive about 200 meters per day, whereas for Curiosity, we could only do about 15 meters per day with full autonomy. One thing that we still don't do on Mars is explicitly recognize, explicitly do terrain classification. So you can see in the lower right, there are a lot of, colloquially, we call them sand dunes. The geologists say it's not sand, it's finer material, so they call them drifts. But you can get stuck in those. The Opportunity rover got stuck in those. Perseverance is still not smart enough to detect those and automatically, it can detect them as geometrically, but we don't do terrain classification on board. Okay, so in the lower right, it illustrates where we did the initial technology demonstration flights for Ingenuity. That straight line down the middle of what we call the flight zone, I think that was 50 meters long. So that gives you an idea of the scale. We were lucky in that where we landed turned out to also be a good place to fly the helicopter. We had contingency plans to be able to drive the rover for a while before we dropped off the helicopter. Fortunately, we landed in a place where we could do that right away. Let's see, now my screen's not advancing again. Either it advances when I don't want it to, or it doesn't advance. Okay, this illustrates that path planner. So on the left, just the notion of all of the red diamonds are rocks and the path planner straddles those. There's a global planner, which is, I think, the field D-star algorithm developed at CMU. So it computes routes on a 200 by 200 map at 1 meter map resolution. And then the local planner is a tree-based planner that searches forward about 3 ply on a tree, and every 25 centimeters or so, it runs something we call approximate clearance estimation, which is the well-known kinematic settling paradigm for testing traversability. And we've got some approximations built into that let it run faster on board. Now the helicopter, just a little personal story about where this came from. So there was research on helicopter flight on Mars back in the late 1990s and through the mid 2000s. People showed that aerodynamically, it's possible to fly in the thin atmosphere on Mars, but there wasn't really a programmatic impetus or support to actually develop such a mission. In the meantime, I started working on autonomous navigation of drones under Defense Department funding here, thinking that someday it might be useful for exploring comets and asteroids. And then in 2013, the JPL director was touring labs around JPL just to stay current on what's going on at JPL. And we gave him a demonstration of some of the autonomous navigation capability we were developing for the Army. he asked if we could do that on Mars, and being aware of that previous research, I said I thought we could. He thought that was quite interesting and started funding a team of us to do design studies, and that eventually led to Ingenuity as a technology demonstration. And now that it's succeeded, we're actively studying how to scale that up so it could actually do science. So a few basic facts about it, you can see on the left. Total mass is about 2 kilograms. It's a counter-rotating coaxial rotor system, 1.5 or 1.2 meter diameter rotors. I won't read the whole slide here, but it communicates through the rover with a 900 megahertz radio link. It's got a solar array on top and lithium-ion batteries inside a insulated warm electronics enclosure. Over on the right, you can see the sensor suite. So we have a downward-looking black and white camera for navigation and a forward-looking rolling shutter camera to send pictures home. There's a small MEMS IMU, a small active ranging altimeter, and then a separating kilometer with less drift that we use for pre-flight calibration of the main IMU. A lot of these components are either from the cell phone industry or other commercial grade components. The processor architecture is illustrated here. So the low-level real-time flight control system uses 2 copies of a dual redundant ARM R5 chip that are lockstep dual redundant. And there's an error bit that basically instructions are compared at instruction level. And if they ever disagree, an error bit is flipped. And since we have 2 copies and a radiation hard FPGA in between, we can run one as a hot spare. So if there was ever a disagreement in flight, we can immediately switch over to the spare flight controller. That ARM R5 doesn't have enough computing to do visual feature tracking that we needed for state estimation. So we have an old, basically smartphone system on a chip processor, which is a Snapdragon 801, that the navigation camera is interfaced to. And so it does visual feature detection and tracking and part of the navigation filter. Low-level state propagation is done on the flight controller. And then the other sensors are interfaced through the FPGA as well as through the controls for the motors. So this illustrates how the navigation system works. Because of computation time limitations on the flight controller and just being conservative about how much autonomy people were willing to trust, we assumed that we would be flying over a level flat surface, and that's built into the estimation algorithm. So it doesn't actually model the 3D coordinates of each feature point. It estimates the vehicle state from the image features and altimetry and IMU data by using the ground plane assumption to give it the third coordinate for all the features. So if this video plays, the video here is from testing on Earth near JPL, and it just illustrates the feature detection and tracking. So we detect features in a 3x3 grid, we track them for 10 frames, and then we repeat. So that just shows that in operation. So that runs on board, and I think it's a 30 hertz update. I actually forgotten that level of detail. It's between 10 and 30 hertz, and we pick up to 100 features and then just track them as long as we can in flight. And those 2 papers you see at the bottom give more details about that. Okay, so Ingenuity got to Mars by being strapped onto the bottom of the rover. During the assembly operations, that picture on the left was taken, so you can see how it was strapped to the bottom of the rover. On the right is a blown up version of the flight zone with the airfield. And here's basically a flight log from the first 9 flights. Video that you may have seen from the very first flight. We started out fairly conservatively, just take off, hover, land, going up to an altitude of 3 meters and not going anywhere, and then gradually getting more ambitious. And so now we go up to altitudes. I think the altimeter max range is only about 15 meters. So we can go up to 10 meters or a little bit more. Flight velocities, I think 1 to 2 meters a second, maybe up to 3 or 4, but we don't go any faster than that. And we're able to fly for about a minute and a half on a battery charge. And as you can see here, that lets us cover up to 500 or 600 kilometers per flight. So we've done actually 17 flights as of last weekend. And since the helicopter communicates through the rover, it has to stay close to the rover. So it's basically hopping along now, keeping up with the rover so that it can help scout routes for the rover as it moves over toward the delta. Okay, so this is part of a sample return campaign. This complicated graphic just illustrates how we expect that to work. So Perseverance picks up samples, puts them in these tubes, and then just drops them off the ground on the ground. The Earth's Return Orbiter, to be built by Europe, uses solar electric propulsion. It'll fly to Mars with that. About the same time, we launched the sample retrieval lander that carries the Fetch rover. Fetch rover, so that's supposed to do pinpoint landing to the sample tubes, go out and pick up the samples, bring them back. Those get put in a orbiting sample container we call the OS that gets launched into Mars orbit. There's a rendezvous operation and a fairly complicated mechanism that hermetically seals the OS inside the Earth entry vehicle. The Earth entry vehicle comes and does a hard landing in the Utah desert. And then we go and retrieve the OS and bring it back to what would be planned to be a level 4 biohazard facility to start processing the samples. And so level 4 biohazard facility is basically the highest safety biohazard lab. And exactly where that will be is still to be defined. Okay, now I'm going to use the rest of my time to talk a little bit about what we think happens next. So NASA has this process called decadal surveys that are done, as the name implies, every 10 years to canvass the science community to formulate scientific objectives for the next decade. And given those scientific objectives, we work backwards to what technology needs to be developed to accomplish those scientific objectives. And of course, this is an iterative process. You have to start with what you believe is feasible, but you need to be pushing beyond that so you know what technology to develop for the future. So this decadal survey process is underway now for the next decade. They're not actually synced exactly to every 2020, 2030. So we'll get the next decadal survey for planetary exploration around next March, and that will cover the decade following next March. In the meantime, something called the Mars Architecture Strategy Working Group was a committee that worked for about a year to develop a vision for what to do next on Mars. And they group science objectives into these 4 categories that you see here. So continuing to study ancient environments and habitability, understanding the subsurface structure and composition. So now that we know that there's a lot of water ice under the surface in the mid-latitudes, that may someday be useful for human exploration. And Mars certainly had a lot of groundwater at some point in its history. It may still have groundwater. If it has groundwater, there could be microbes down there. So one goal is to find out if it has groundwater, and if it does, eventually to drill kilometers deep down there to see what we find. We'd like to continue to understand the climate on Mars. If we go land on the poles, we can begin to understand the recent climate changes. So Mars obliquity varies from near 0 up to 45 degrees or more over roughly 120,000 year cycles. And that shifts the ice from the poles to equatorial areas, a very important part of the history of Mars climate. So we'd like to understand that more. And understanding atmospheric processes and climate variability is part of the whole big picture. So how do we do that? Well, that story to some degree gets wrapped up with interests at the moon. So let me talk for a minute about the moon. So there's a lot of interest in the US and elsewhere now about sending people back to the moon and doing more robotic scientific exploration of the moon. There's a rover in development called Viper that's supposed to launch in about a year to land near the South Pole to explore for shallow water ice resources on the moon, which would be important if we send people there. There are several mission concepts for very long range rover missions to do science on the moon. So one concept called Intrepid would send a rover that over the course of 4 Earth years would travel about 1,800 kilometers to visit locations that would let us study 4 billion years of lunar geologic history. So when you compare that distance to what we've done on Mars to date, I've actually forgotten. So Opportunity drove, I think, around 49 kilometers in 14 years. So you can see that this is 2 orders of magnitude farther in less than a third of the time. So that's significant. There's interest in more extensive lunar polar subsurface ice mapping, including going into permanently shadowed regions in craters near the South Pole. And there's also interest in using rovers to collect samples to bring back to Earth. One of the reasons for that is what we call geochronology, so that we could actually get accurate, absolute dates for formation of those samples. And that would be very important to calibrate essentially the history of processes that form the surfaces of rocky bodies. And right now we estimate all that from crater size frequency statistics, but that's prone to error. So against this backdrop, we look at what we would like to do for Mars. So on the right, by the way, is an illustration of a lunar rover concept for that Intrepid mission. So all of this led us to wonder, what could we do by way of long range rovers on Mars? And so I have a paper that's going to appear about that at the IEEE Aerospace Conference in March. And we think that in the course of a few years, if we did the right technology development, we could probably enable rovers that could cover at least hundreds of kilometers in a few Earth years on Mars. And so that paper will talk about what might we do scientifically with that capability. One of the most important things that we would need from a robotic autonomy perspective to do that is onboard absolute localization, so that we can tell as the rover drives where it is. We've been working for a little over the last 3 years on concepts for next generation aerial mobility on Mars. So this is a collaboration between JPL, the NASA Ames Research Center, and AeroVironment. You know, those three organizations collaborated to develop Ingenuity. So what we're looking at is down in the lower left is an illustration of Ingenuity. So we're looking at now a hexcopter that in the fully deployed configuration would be about 4 meters from tip to tip. The rotor blades themselves are about the same diameter as the Ingenuity blades. We need more advanced computing and sensing for this. It would again be solar powered with a lithium-ion battery. Our modeling of flight performance is illustrated in the graph in the upper right. So that depends on atmospheric density, which depends on elevation, depends on latitude, because that determines how much solar power we've got. So this particular graph was done for conditions at Jezero crater. And what you can see is that we think we could carry payloads of up to about 8 kilograms if we had very short flight times. But what we've been thinking about currently is payloads of about 5 kilograms. And there we think that if we spent all of our time hovering, we could hover for about 4 minutes. Or if we spent all of our time flying, we could cover about 10 kilometers of range per flight and then recharge the battery over the course of 2 or 3 days so that we could fly again. And so with that, we could do helicopter missions that could be potentially hundreds of kilometers. Challenges to enable this, we'd like to have a helicopter that isn't tied to a rover or a lander. So we would need to be able to do communication by relaying directly to orbit. We need autonomous navigation for long-range missions. So we need to generalize the state estimator to be able to fly over arbitrary terrain. We've done a lot of work on that and published some papers on that. We need to do onboard landing hazard detection. We've been working on doing that with visual structure for motion. We've had a paper or two come out about that. And then we also need to do onboard absolute position estimation by in flight, and the technical approach we've been using for that is key point matching. So basically create a database of landmarks, which are key points in the orbital imagery, and then register those to key points on board in real time from navigation imagery. And that needs to be done in a way that's fairly insensitive to lighting variations. That's possibly interesting topic for ongoing research. We need more onboard computing, so we're looking at more recent cell phone class onboard computing. To do a real science mission, the standards for reliability are much higher than they are for a technology demonstrator. So we're very gratified that Ingenuity is doing so well, but we need to build in more fault tolerance before NASA would spend hundreds of millions of dollars on a science mission. So that requires redundancy in the avionics, which has implications for mass. And then to make this all affordable, we'd like to do mid-air deployment. So as the system is descending with a parachute to the surface, we'd like to drop the helicopter out and have it begin flight in midair, because then we wouldn't need to actually have a lander, which would add a lot more cost. So there's work in progress on that. And in fact, NASA's developing another mission right now you may have heard about called Dragonfly for Titan. So that is led by the Applied Physics Lab, which is part of Johns Hopkins University. They've been working on this for a couple of years now. Some important differences are, first of all, Titan has a lot more atmosphere. So its atmosphere density at the surface is about 4.4 times Earth, whereas Mars is 1% of Earth. It's also got lower gravity, so the gravity is about half of Mars. So all of that makes it much, much more favorable from an aerodynamics perspective for flight. There's a lot less energy available. So the surface illumination on Titan is about 1% that of Earth. And it's very cold, it's 94 Kelvin. To do a useful amount of science, you need quite a bit of instruments. You need a heavy vehicle. So they're looking at something like 450 kilogram vehicle that uses a radioisotope thermal generator for power. That's an artist's conception of it. And their concept for mid-air deployment looks like this. So with that thick atmosphere near the surface, their vertical velocity at the time they release the Dragonfly would only be about 2 meters per second. And they have a fairly sophisticated sensor suite with a LiDAR, downward looking and forward looking stereo. So that LiDAR is actually an imaging LiDAR, so that's for hazard detection. There's also a radar altimeter, a navigation grade IMU. And the plan is to land in a large dune field. So they'll know they're heading during descent and drop out of the back shell at about 1 kilometer altitude, and then turn to head perpendicular to the dune crests and use the altimeter and or the LiDAR to figure out when they are over an interdune region between dunes, which are pretty flat, and land there. and then continue the rest of the mission. So that's a little bit about Dragonfly. My last slide here is just a quick discussion of another difficult, robotic perception and planning challenge for Titan, which is, could you do precision landing on Titan if we ever need to? And if so, how would you do it? So how does this entry, descent, and landing process differ between Mars and Titan? So on Mars, it all happens very fast. We enter the atmosphere at a very shallow depression angle of about 7 degrees before horizontal. We spend about 4 minutes in the entry phase when we're inside the aeroshell. Then we deploy the parachute, and we spend about 2 or 3 minutes getting to the ground. The error is dominated by the entry phase because of that very shallow entry angle. We can see the surface pretty clearly from orbit, and so therefore we can do that terrain relative navigation thing I talked about, and we can detect all the landing hazards from orbit. Titan is very different. So we enter at a much steeper angle, but the atmosphere is much taller and much denser. So the entry phase is also about 4 minutes long, but we deploy the parachute at 150 so kilometers above the ground. And then it takes us at least an hour and a half to get to the ground. And in that time, with the high winds, we accumulate a lot of position uncertainty. So that means that the major axis of the landing error ellipse is 100 to 400 kilometers long. And that's not due to error in the entry phase, it's due to uncertain winds while we're on the parachute. And that atmosphere is also very hazy, so we can't see the surface very well. So the best imagery from orbit is imagery at a resolution of 1 kilometer or more per pixel, or radar data at a resolution of about 350 meters per pixel or more. So we really can't map landing hazards from orbit. And we have pretty poor remote sensing imagery for map-based position estimation. So we did a couple years of work on that that we presented at the IEEE Aerospace Conference 2 years ago on how would you do position estimation. And to get the control authority to do precision landing, you probably don't want to use rockets here. You probably want to use some kind of guided parachute or parafoil. So we studied that as well. If you're interested, you can look up the papers that are cited below. So thank you for sticking with me if you're still there, and I'm done and happy to take questions.
Wonderful. Thank you for a really interesting talk. So we have, I see a question, or one person with some questions in the chat. I'm happy if you would like, I'm happy to read them out to you, or would you like to read them out yourself? It's whatever works best for you, Larry.
Let me see, I don't have the chat up,
okay.
So it's easiest for me if you don't mind reading them.
Not at all. So I'm going to start with the second one first, which is, what's the most limiting factor for the onboard computing? Is it, or just example, is it the power? Is it autonomy? Is it the radiation hardening? Why do we have such slow computers?
It's really the radiation hardening. That's an expensive and time-consuming process, and it's a small market. So, there's not many people that want to pay for that kind of thing. And the community is cautious and conservative, so they hesitate to use new technology until somebody else has proven it out first. But it turns out that the surface of Mars, is relatively benign compared to most places in the solar system, because you do have some atmosphere and you've got the planet that shields you for 2 pi steradians. So on the surface of Mars, there's more, or it's more easy to use commercial grade electronics than it would be in deep space or at places like Jupiter.
So for the radiation hardening, how much of it is it modifications to the design, and how much of it is it just characterizing the radiation performance of existing hardware?
Well, it's both. So it's a long story. I'll try to keep it short, but there are multiple failure modes. So there's something called latch up, where you have a permanent failure, so a component burns out. And then you can have a variety of types of soft errors where an energetic particle goes through the silicon and flips a bunch of bits. So latch up, you really have to solve with the hardware design, so you don't have permanent failures. The soft errors, you can either solve by hardware design if you use very large transistors, for example, that are resilient to that, but then you're limited to very old, slow technology. Or you develop software techniques to cope with soft errors, or you have redundant hardware. So, Ingenuity has basically 4 copies of the ARM-R5 that are redundant, and so we cope with soft errors that way.
Okay, and so then the second question is, do you see a possible use for legged robots on Mars? So for example, maybe the drifts you were talking about or rough terrains.
So there's, people have studied that a lot. For Mars, I don't think so. Legged robots are, great for extremes of terrain, but they're less energy efficient than wheels. And I think all of the science objectives that I know about so far can be done with wheeled rovers. And so we don't have a strong motivation to use legs on Mars.
All right. So anyone else, feel free to pop in questions to the chat. I had one about the steering during the entry with the active steering with the lift. That's still when it's got the full aero shell on it. Is that correct?
That is correct.
So what's the input to the steering? Is there imaging available, or is it purely just integration with IMUs from the imaging of when it started the descent phase?
It's just IMU. Yeah, it's IMU integration. The way it knows where it is at the beginning of entry is a combination of radiometric tracking from Earth and then what we call optical navigation. So there's a camera. As it approaches Mars, it takes pictures and it basically looks at where is Mars and where are the moons of Mars. And that's another input to basically position and velocity estimation during Mars approach.
Okay, and then the source of the error during that, the source of the error that you're controlling for is result of the physical processes, not of error in measurement, I guess. And that's why you can just integrate the IMU's measurement during that phase of the descent.
Right. I think most of it is actually uncertainty in the density of the atmosphere.
Okay.
And the variable density, then also the variable height of the atmosphere. So I think that's the biggest source of error.
All right. Does anyone else have any questions? If not, I think we're doing a pretty good job of ending on time. One more, at least one more question. Right. Oh, this is a great question. So how do Perseverance and Ingenuity keep track of each other on the surface, as the odometry navigation on both will drift? Are they relocalized using the orbiter?
They are. So the way we do relocalization right now is we send images from the vehicles to Earth. And then we have interactive software on Earth where we can overlay those images on the orbital data and register them that way. So, we're working to move those algorithms on board, but right now we do it on Earth with images that we send home.
What's the roughly how long does that process take? That must be days, I assume? Between the transmission windows and.
Well, we could do it in a one-day turnaround. So there's enough orbiters at Mars right now that we've usually got 2 or 3 opportunities per Earth day to send imagery to Earth. It takes between 10 minutes and half an hour to transmit that data to Earth. And then once it's here, it would take somebody half an hour to generate the position estimate.
Okay.
So we could do that update on a daily basis if we need to.
Right. Okay. So another question is, how do you plan to locate and collect the samples that Perseverance is dropping off if they get buried with dust in the decades between now and pickup?
Great question. That's something that people looked into a lot. And the conclusion was basically, Mars is an active planet, but we don't expect enough dust accumulation to bury them between now and when we hope to get there to pick them up. And I think that conclusion is probably robust, even if our plans change and it takes us much longer to get there. So, there will be some dust that accumulates, but not enough to bury them.
Okay. Is the low level acquisition or detection vision, or is it being left with like beacons or anything like that to help the sample return rover find it?
Well, there would be two things. So one is we should know very accurately where we put them down, because we've got this localization process. So we should know where the samples are, to within a meter. And then by using the same thing, the next rover can get to within a meter. And we expect that, finding the samples at that point will be visual, just using camera imagery.
Okay. So last call for questions. If not, I think, all right. Is the dust on Ingenuity's solar panels limiting factor to its expected life at all?
Another great question. So that was something that we worried about during development. We thought there was a good chance that the airflow from the rotors would blow the dust off every time it flew. And the evidence so far seems to be that that's happening. So we're not seeing dust accumulation on the solar panel, which is quite a bit different than what happens with the landers and the rovers.
Right. Can you share any plans for Ingenuity's is there any plans for how much longer Ingenuity will continue to be used on Mars, or will be able to continue to be used?
Well, how long it will be able to be used, there are no consumables. Right. So it's either until something breaks or we have a bad landing. We've asked for funding and authorization to operate it, I think, for the rest of this fiscal year. So that means through next September. That's not approved yet, so I don't know, but we think that's likely to happen. And if the scientists continue to feel that it's valuable, that might continue. It takes money because we have to pay the team that operates it. So it's always, a trade-off. Is there enough value to keep paying for it? And for at least the rest of this year, the belief is yes.
Okay.
Well, the belief is yes, but it's not a formal decision by the powers that be yet. So we're waiting to find out.
Right. Okay. So hopefully this isn't a sensitive question. How are the current wheels holding up compared to the problems Curiosity had?
So if you're asking, I'll answer two questions. So Curiosity, they changed how they operated it to really try to baby the wheels. And Curiosity's mission will be limited by the lifetime of the radioisotope thermal generator. So we think that the wheels will survive for the lifetime of that. And I'm not sure, but it's probably got 3 or 4, maybe 5 more years to go before it doesn't have enough energy to drive anymore. And then Perseverance, they made stronger wheels. So they're heavier, but they're stronger. So we don't anticipate problems with Perseverance's wheels.
Excellent. Unless there's any last breaking questions, I think that should be it. We've very much appreciated your time. So thank you for what I think was a really interesting talk. And hopefully we'll see some of our guests back at the next month's seminar. So thank you very much.
Thanks again. Good to see you. Bye.
Take care, everybody.